This is a lecture on research plumbing, the first of two. And in this final segment of the lecture, I'm going to be showing you how to make some really nifty tables with minimum effort using the model summary package. But before I can do that, I would like to introduce a data set that we'll use to make the tables. This data set comes from the STAR project, not to be confused with the Star Wars example from earlier in the lecture. STAR stands for Student Teacher Achievement Ratio. This was a 4-year longitudinal study that was carried out in Tennessee, in which over 11,000 students were randomly assigned to classes of different sizes. And the research question of interest here was whether the class size in early grades of school actually matters. Does it have any effect on later outcomes? If you'd like to learn more about the paper, you can go to the course website, detrali.com/ERM, and find the slides for this lecture, which is Research Plumbing 1. Then click on this link, and you'll be directed to a paper by Mosteller about the results of the STAR project. But for today, it's enough just to know which variables are contained in the data set. So the variables we're going to talk about are race, a student's race, class type, which is the type of kindergarten class, more in a moment, G4 math, which is the student's math test score in 4th grade, so that's an outcome variable, G4 reading, also an outcome variable, that's the reading test score in 4th grade. Years small is the number of years that the student spent in small classes. And HS grad is a dummy variable that equals 1 if a student graduated from high school. That's another outcome variable. All right, I have stored a copy of this data set on my website, so we can load it in using read_CSV from Reader. And wow, it's a bit of a mess. If you take a look at the race column, what do we see there? We've got 1, 2, 1. I don't know what those mean. How are we supposed to know what race 2 means and what race 1 means? And what about class type? What are these 3s? What's this 1? What's this 2? This is bad. This is bad because the data set alone is not enough to tell us what on earth is going on. So when you're storing your data, you should always try to think about ways to make the data set self-documenting if possible, ways to make it really obvious what the columns mean. I'll just give you one example. If you have a column called sex and it contains the values 0 and 1, how do I know if 1 is male or female? It would be better to call it sex and make sure that it contains character strings that indicate male, female, or whatever other category you wish to put in. So what we're going to do here, before moving any further, before making any tables, is recode the data set so that it's obvious what each of these columns means. That will actually make our tables a bit nicer too, because when we compute summary statistics and so on using model summary, it will be able to use the information that we put into the race and class type columns to make a nicer table. So here is the information on what is contained in each of those columns. It turns out that the race column is coded as follows. 1 is white, 2 black, 3 Asian, 4 Hispanic, 5 Native American, 6 others. Class type is 1 for small, 2 for regular, and 3 for regular with a teacher's aide. High school grad is 1 for did graduate and 0 for did not graduate. So how can we recode these? Well, it's quite easy using the case_match command from dplyr. So in this code block, what I'm going to do is I'm going to use a mutate statement to create a column called class type. So I am overwriting the original class type column. And to construct my class type column, I'm going to use case match. So how does case match work? Well, the first argument to case match is the column I want to work with. Here it's class type. And then I have statements of the form something, tilde, something else. So the thing to the left-hand side of the tilde, here 1, is a value that I want to recode. So I want to recode in the class type column a 1 to become the string small. I want to recode a 2 so that it becomes the string regular. And I want to recode a 3 so it becomes the string regular plus aid. And you can see that after I run this command, I'm overwriting my original star data set. So I display it here in line 6, and I get exactly what I want. So I now have a column class type in which the entries actually tell me which type of class it was. I have a very quick exercise for you. You don't need to stop the video. Well, you should stop the video for a moment, but I'm not going to create a second segment. So please recode the race and high school grad variables from star as indicated above, following my template on the previous slide. You can hit pause now, and when you're done, resume to see the end of this segment. All right, so now we're finally ready to make some nice tables. Here are some possible ways that you could make a table. I have helpfully ranked them in order from worst to best. You may think I'm joking for number 1, but I've actually seen students take a screenshot of data output, stretch it so the text is distorted, grainy, and totally unreadable, and submit it in their master's thesis. Needless to say, I do not suggest that you do the same. Slightly better, but still terrible, is to copy and paste individual results into an Excel table, edit them manually, and then paste that into a Word document. While slightly better than screenshotting, this copy and paste approach creates so many opportunities for error, at the same time as it makes it almost impossible for you to replicate your work. What if the results change? Do you really want to copy and paste and edit manually again? By the time we get down to 3, things are starting to look a bit better. So you may know that there are some packages that can, for example, automatically export data results into Excel. And you may think, oh, that's good, because then I'll manually edit in Excel and then paste that into a Word document. That's a bit better, but this is still incredibly cumbersome. Do you really want to manually edit the table every time that the regression results change? And you've still always got the risk of pasting the wrong results into your Word document. Well, needless to say, you should not be using Microsoft Word or Excel for anything at any point, and you should be using reproducible tools. For making tables, I recommend that you take a look at Empirical, GT, and Model Summary. Of these, Empirical is fast and dirty, but useful for lots of purposes. GT is extremely elegant and refined. It gives you total control over how your tables work. And Model Summary is some kind of a compromise that can be combined very nicely with GT that tries to give us really nicely formatted tables with a minimum of effort, and most importantly, it allows us to automatically include them in any document format. So these are particularly useful when combined with Quarto and R Markdown, which I described in the first segment of this lecture. Today, I'm going to talk about data summary and Empirical, which data summary is part of the model summary package. In future lectures, I'm going to talk about the model summary command. Now, some people prefer a package called Stargazer. It does very similar things to model summary. That's fine. You can use that if you prefer. I think model summary is more flexible and more helpful. And again, if you want the ultimate in precision table creation, you should check out GT. All right, the first command from model summary that I'd like to show you is data summary _ skim. This takes a tibble as an argument and produces a really helpful table of summary statistics. Look how easy that was. We've got the variables years small, G4 math and G4 reading. We see how many missing values there are. We've got means, standard deviations, min, median, max. We've got a cute little histogram for each variable over on the right. If you don't want the cute histogram, you can set the command histogram equal to false. And very helpfully, data summary skim has not given us extraneous decimal points. So it does provide some decimal points, but unlike the tables that you'll sometimes see in published work, it's not giving us 9 decimal places when our standard deviation is 43, which would be a bit silly. It's doing something moderately reasonable. And if you read the help file for data summary skim, you can see that there are ways to customize all of this output. What I'm trying to point out to you is how easy it was to get something that looks pretty good with effectively no effort. You may notice, however, that data summary skim dropped all the categorical variables. that's because standard deviation and mean don't really make sense for these. This is another pet peeve of mine when I look at published papers. People often report, let's say, the mean and the standard deviation of a binary variable. Well, I've got news for you. Those are not actually two separate degrees of freedom. The one completely determines the other. So what data summary skim actually does is it treats categorical variables differently. So if you have a string or a factor, it just does the right thing. And this is actually the reason why I asked you to recode everything before. Because if you were to use numbers, as in the original star data set, data summary skim wouldn't know what to do. It would say, oh, race can be 1, 2, 3, or 4. I suppose it makes sense to compute a standard deviation for race. Whereas in fact, we know that's silly. So by recoding the variable, we made it much easier for data summary skim to help us out. So to obtain a table with the categorical variables, we're going to use the command data summary underscore skim star comma type equals categorical. So the first argument, again, is the tibble that we want to summarize. And now we're supplying an argument that tells data summary skim we'd like a table of all the categorical variables. And here it is. So you can see that for each variable, it has broken it down by category. It has told us the number of individuals in each category, along with the number of missing values. And it's also helpfully given us the percentage of observations in that category. Another common sort of table that you will see in published papers is sometimes called a balance table. I have views about balance tables, and if you ever want to buy me a beer and hear them, I'll be happy to talk your ear off for an hour. However, they can be useful in some cases. So I don't want to completely denigrate the balance table. Roughly speaking, what a balance table allows you to do is compute summary statistics by group. So you're going to supply a grouping variable, and you do this using the syntax tilde, and then the name of your grouping variable over here, and then comma, supply the data. So what I'm going to do here is I'm actually going to use one of the fun properties of the R's native pipe. So you may remember that the native pipe that was introduced in R version 4.1 has another handy feature, which is this underscore for supplying another named argument. That was I believe that was introduced in R version 4.2. So what I'm going to do here is I'm going to select some columns, years small, G4 math, G4 reading, and class type. Then I'm going to pass these in as the data argument to data summary balance. Isn't that fun? Using the underscore syntax. And then I'll supply class type as a grouping variable. So what this will do is it will produce summary statistics broken down by class type, which in this case is pretty handy because class type is exactly what was randomized in this experiment. So what you can see here is we get a nice table that shows us the three values of the grouping variable: regular class size, regular plus an aid, and small. We see how many students were in each group, and then we have summary statistics by each of the groups. So what we're looking at here is the outcome variables G4 math and G4 reading, as well as years in a small classroom. Look how easy it was to get a table that's almost as good as ones that you see in published work. If you use the right tools, you can make everything so much faster, so much cleaner, and so much less error prone. Now, data summary skim and the related functions that I've just shown you are very helpful, but sometimes you want a custom table and you want something that's fairly simple. Here is a prototype example for you in which I am going to construct summary statistics of grade 4 math and grade 4 reading, in particular the means, broken down by class type. So I'm doing this using some of the handy dplyr skills that I've picked up from core ERM. I'm using a group by statement to form a grouped tibble in which the grouping variable is class type. Then I am going to summarize by that grouping variable. And I'm going to use the across command that we met earlier in this lecture to first of all specify the columns I want with a tidy select operation here, and then to apply the function mean na.rm equals true to each of those columns. And finally, I'm going to use the naming syntax from the glue package to give these columns some nice handy names. So that produces a tibble. It's a relatively clean little tibble, but I might like to produce something that's a bit prettier for appearing on a slide that doesn't just look like typewritten output. And that's very straightforward using the command knitr cable. These two colons here are a way of telling R that you would like to use the command cable from the package knitr without actually loading the package knitr. So everything after the column is a function name, everything before is a package name. This is an alternative way to refer to a function in a package that you have installed, but you have not loaded. And the knitr cable command is quite simple. It allows me to specify all sorts of things. But what I'm doing here is I'm using the pipe to supply my table as the first argument to knitr cable. So I'm supplying this tibble, which is then going to be turned into a nice table for me. I'm specifying how many digits I would like, how many decimal points. 1. Please don't use extraneous digits. It's something that makes me cry. And the less crying I have to do, the better on the whole. I'm also specifying a caption, average grade 4 test scores, and column names. And you can see at the bottom of the slide, it produces this relatively cleanly formatted table that doesn't give perhaps quite as much information as the one on the previous slide, but it might be good for a simple example in a paper. That's it for Research Plumbing 1. If you enjoyed this lecture, I bet you can't wait for Research Plumbing 2. But our next lecture is going to be about linear regression.